Hello everyone. Today we study sum of property in convergence for Fourier series. And last time, we studied Gibbs phenomena that happens when the given function f is not continuous. Okay, so we use the example a jump function, and then we studied the Fourier series does not converge uniformly to the given function when the function f jumps at some point. Okay, so today what I'm going to prove today is that so I wrote down here two theorems. So theorem 1, suppose if f is continuous and f pi and f minus pi are the same. So we can extend this function to the periodic in whole space, right? And then another assumption is that f prime is piecewise continuous. Okay, if if f satisfies these three conditions, then we have the following properties. Number one, square root n equals 1 to summation n equal 1 to infinity, square root a squared and b squared, this converges. The property A we actually proved in lecture 5, so you can look at lecture 5 again. And then B, what we're going to prove is that the Fourier series is actually converges absolutely and also uniformly to given function. Okay, so we have three conditions. And then number 3, if second derivative of f at x exists, then you can differentiate a Fourier series, and this is actually converged to f prime x. Okay, so if f the f double prime f double prime does not exist, then we have we have two conditions, and then we have a right derivative or the left-hand derivative exists, then this one is obviously converged to 1/2 f plus prime, and then f prime minus. Okay, so this is actually the number 3 is actually consequence for this is by Fourier theorem. Fourier theorem you can apply for f prime x. Okay, so we don't need to prove this one, which I just write down here. And this is one theorem A. So all we need to do is we need to prove 2 and 3 in the first part. The second part is consequence of Fourier theorem. We proved in the previous lecture. And then I stated here theorem B. What is theorem B? Theorem B is that if we don't have more conditions, so we have condition f is only piecewise continuous on minus pi to pi, then the Fourier series is actually, you have a Fourier series for f, then you integrate the f, it's the same as integral of Fourier series. Okay, so the given function and then Fourier series, the given function and Fourier series, so they are different at point. Okay, so does not this one converges, some point x converges to fx, some point does not converge to fx, but global property. So when you have integral minus pi to t, this one gives global informations, not local information. Okay, global information. So global. So I can say that in the theorem B as globally f of x and Fourier series, they are the same. So that I can pretend, okay? I can interpret it like this one. Okay, anyway, we are going to prove these two theorems today. So first, let me try to prove first theorem, proof of theorem A. So I mentioned earlier that the property number 1 is actually, you can see lecture 5. So summation m from 1 to infinity square root a n squared and then b n squared. This is finite. Okay, so remember what we used here. So f prime is piecewise continuous. Then we used Fourier series for f prime. So let me just rewrite. Remember, okay. So we need this one later. So let alpha 0 over 2 plus summation m from 1 to infinity alpha n cosine nx plus beta n sine nx. Okay, so let this one be the Fourier series for f prime x. Then what we have, alpha n, by definition, 1 over pi minus pi to pi f prime x cosine nx dx. And then using integration by part, and then we use property f pi with end. We used f pi minus pi. Then I remember when you do this one, that would be 1 over n f x sine nx, and then minus pi to pi. So this 1 over pi, and then minus cosine. So that would be 1 over n integral minus pi to pi minus pi to pi. So this one fx, I'm sorry, this should be cosine. This should be cosine nx, cosine nx, and then this would be sine nx dx. Okay, so that's what we had before. And using this property, this becomes 0. So that would be minus 1 over n, 1 over pi, integral minus pi to pi, f of x sine nx dx. So this is actually 1 over n bn. So where bn is a coefficient for Fourier coefficient for f of x. Okay, so this is the one you need to remember. And then also beta n is 1 over pi integral minus pi to pi f prime x sine nx dx. Again, you're using the integration by part and the same property. So 1 over pi, that would be minus 1 over n cosine nx f of x. Okay, and then I put minus pi to pi and then minus, and then you got the derivative should be plus, that would be 1 over n integral minus pi to pi f of x. Let's see, this one fx. I'm sorry again, here, let's see, here, not, okay, here, fx, so here, I'm sorry, this should be fx sine nx, not cosine nx, and then here cosine nx dx. Okay, I got big parentheses here, and then you plug pi minus pi, this becomes 0 again. So finally we have 1 over n, 1 over pi integral minus pi to pi fx cosine nx dx. Okay, so that would be 1 over n an. Okay, so you need to remember these relations. Okay, so alpha n and beta n equal 1 over n. Okay, so we use this property to prove this one, but we are going to use this one again in some later. Okay, and then part B. Part B is easy. So once you have a part A, part B is easy. So part B. So what is Fourier series? The Fourier series is this summation n from 1 to infinity an cosine nx plus bn sine nx. So we need to show this one converges absolutely. So this converges absolutely to f of x. So this is a part, so we prove this one first. So by the way, by Fourier theorem, you apply Fourier theorem. So this guy is actually converges cosine nx bn sine nx. This one is converse. Is it converse? Let me check. So f prime is piecewise continuous. That implies for each point you have a right derivative, left derivative exists. So this guy converges to f of x. Okay. So because f is a continuous function, so this is a continuous function. And then we want to show this one, the absolute converse. So let me erase this part. Okay, I'm sorry. Absolute converse means just you make absolute value. So you got the a0 over 2. So our claim is to show that absolute value of this, and then summation m from 1 to infinity an cosine nx absolute value bn sine nx. So we need to show this one converges. This one converge means absolute converge. Okay, let me rewrite. Okay, absolute converge. Yep, absolute converge. But this is easy. So this is easy because, well, this is just constant we don't worry about. But I compute the second part only. This guy an cosine nx plus bn sine nx. Okay, so for each term, this guy is less than summation m from 1 to infinity, absolute value of n, and then bn. Okay, and each term is less than square root an squared and then bn squared, and then you make twice of this one, and then this is exactly 2 times this guy's oops, let me change color. Okay, that's 2 times summation m from 1 to infinity square root an squared bn squared. This is just finite, okay, by part A. Okay, so that means this is converged absolutely. So we are done. And the second part is just also very easy. So in order to prove second part, we use wire stress M test. So you can apply wire stress M test. Okay, so what is that? You just remind that let fnx is less than mn. Okay, for each x, well, some e. Okay, e is just the subset of R, some subset of R, and then summation m from 1 to infinity, mn is converged, it's finite. Okay, this is mn is constant. Okay, this mn is constant, independent of x. So then summation m from 1 to infinity fnx, this guy is converged uniformly. So I hope everybody can remember this. If you don't remember, then you can check the property in some real analysis or some advanced calculus course. So you can apply this formula. Okay, then we already have this one. So in the part A, part 1, we already know that the A0 over 2, this is a Fourier series. So this is a Fourier series. an cosine nx plus bn sine nx. Okay, this is Fourier series. And then I call this guy's f. Look at here. Each term, an cosine nx plus bn sine nx term. Each term is less than 2 square root an squared and the bn squared for each n. So, and then we know that, so this is, we call this the mn. Okay, mn. This is the mn in order to apply wire stress M test. This is the wire stress M test. So, and then we know that by part 1, we know that summation m from 1 to infinity square root an squared bn squared is finite. Okay, then by wire stress, so wire stress M test. So you have A0 over 2 plus summation m from 1 to infinity an cosine nx plus bn sine nx. So this is converged uniformly. Well, we already proved this one converged to f, so uniformly to f of x. So this is how we proved. So basically, this is just the consequence of just the part A part. number one, part. Okay, consequence of this part. This one gives you that the Fourier series actually converges absolutely and also uniformly to f of x. So, and then so far it was very easy part, and then we are going to prove part C, part 3. So proof of part 3. Proof of 3. Oops, something strange. I don't like this one, so let me erase. Okay, so let's try to prove 3. Okay, now if we assume that second derivative exists at one point, assume that f double prime x exists, then what we consider in this case, so what we want to prove is that we want to prove the derivative of f of x, and then you can differentiate original Fourier series with respect to x, and then we can differentiate f double prime. We compare two. Then let alpha 0 over 2 plus summation m from 1 to infinity alpha n cosine nx plus beta n sine nx. Suppose this is the Fourier series. For f prime x. Okay. Then, so now, just a note that I want you to remember that. So f double prime exists. That implies f double prime positive x, f double prime negative x. This is actually exists, right? They're the same, okay? They are the same and exist, okay? They are the same and exist. And then you can apply Fourier theorem, that by Fourier theorem again, Fourier theorem. So this Fourier series actually converges to f prime x. So this guy alpha n cosine nx plus beta n sine nx. This guy converges to f prime x. Okay? So this is consequence of Fourier series. Now, what is alpha n? Alpha n, so this is, what was alpha 0? So let's compute alpha 0. So alpha 0 is 1 over pi integral minus pi to pi f double prime x. And then we know that f pi equals f minus pi. So f pi equals minus pi, condition 2. So this becomes 0. This one 1 over pi f pi minus f minus pi. So this becomes 0. It's gone. Okay, so this becomes 0. And then let's compute alpha n. You can compute alpha n. That was 1 over pi integral minus pi to pi f double prime cosine nx dx. Okay, now let's go back to the proof part A. What we had here, So we already computed the relation between an, so alpha n is the Fourier coefficient of f double prime. So this alpha n equals 1 over n bn, right? Beta n equals 1 over an. Okay, so this is what we had. So we already have, so this alpha n was minus 1 over n bn. So minus 1 over n bn. So it would be minus 1 over n bn. And then beta n equals to 1 over n an. Okay, this is what we had. Okay. One over n. Let's see. Do we have the same beta n, alpha n, beta n, 1 over bn. Alpha n. I'm sorry. So here I made a mistake. So it was a little strange. So I made a mistake. This should be not n. So this is this one. This should be n. Okay, differentiate. You differentiate, right? So it was a little strange. So then this should be n, and this is not alpha n. This is minus n bn. Here again, this should be none. This should be n. Okay, so this one should be n. So I applied integration by part, a little bit mistake here. So that should be n times an. Okay, now, yeah. So then this is not this one. So I need to correct. This is minus n bn. Okay, so beta n equals to beta n equals n an. So this is how we got. So therefore, hence, so then oops. So then I have this is 0. You plug in here, so that would be n equals 1 to infinity. So alpha n is minus n bn cosine nx. Okay, plus n an sine nx. So that's what this one converge to f prime x. So this is what we have here. Okay, so let me circle this part. Let me circle this part. So what is this series? So you actually differentiate this part. This differential this part, you can differentiate. Then 0, and then you have n equals 1 to infinity. Derivative with respect to x, you have minus nan cosine nx, or sine nx. Okay, you have sine nx. And then here n, bn, cosine nx. That's exactly this one. Okay, so this is done. We proved derivative converge to where is it? Our part B. So this guy is actually derivative of Fourier series. Oops. Okay. So that guy is derivative of this guy derivative of Fourier series. So we proved part A. Okay. So now let's move to prove part B, the theorem B. Proof of theorem B. Okay. So B, we only have f is piecewise continuous. That's what we all have, right? So we have all the information is piecewise continuous. On minus pi to pi. Oops. X pi. And then and also let a0 over 2 plus summation m from 1 to infinity an cosine nx plus bn sine nx. Okay, so this is the Fourier series. So this is the Fourier series for f of x. Okay, now I'm going to define large fx to be integral minus pi to, let me change, let's say t. So t and then t fx dx. So let's define like this one. Okay, then so then what you can see is this guy f is piecewise continuous. Then f is actually continuous function. So f is continuous. So then t between minus pi to pi. Then we know that f is continuous. Continuous. Let me also put this one. We don't need to worry about. So t is continuous. And let's compute f pi. So f minus pi equals 0. And then f pi equals, what is that? So integral minus pi to pi fx dx. So this is actually 1 over pi, a0 was 1 over pi integral minus pi to pi fx dx, right? Fx dx. So this one would be just pi times a0. Okay, that's what we have. And also, let's see, f is piecewise continuous, and you can, and also piecewise continuous. You can also show that f prime equal is piecewise continuous. Okay, piecewise. So if integral piecewise continuous means, suppose you have a function minus pi to pi, piecewise continuous, then you have like this. This is piecewise continuous, and the on continuous region, this guy is differentiable, and then that's why this is true. This is piecewise continuous. That's the property of integral. Okay, this is a very important property. Okay, when you study integral, so piecewise continuous. So you can apply sort of what? You can consider the Fourier series for f prime, right? That's what we can do. So now, in order to use the Fourier theorem, so what we need to do is we sort of want this one to be, we want, so one condition, we need f pi equals f minus pi. So this is what we need. But somehow here, f minus pi equals 0, f pi equals pi a0. So we need to define new function f tilde to be satisfy this one. Okay. So what I need to do is I can replace f by. So now we define the f tilde t, define integral minus pi to t fx dx, and then I put a0x. So when you look at this function, 10t, so t, then you see that then f tilde is continuous, and f prime is piecewise continuous. So this is piecewise continuous. Furthermore, f tilde pi. What is f tilde pi? Minus pi. Tilde minus pi, you plug here f tilde minus pi. First integral 0 minus pi I0 pi. This is what we have. This is minus a0 over 2 pi. Okay. And then you compute f tilde pi. Minus pi, this is 0. So pi, then you have integral minus pi to pi fx dx. When you put pi, a0 over 2 pi. Okay. Minus pi, you got plus. This is plus. So here, and the first part is a0 pi minus a0 pi divided by 2. That would be a0 pi over 2. They are the same. Okay. So they are the same. Then I can compute the Fourier series for f tilde. So let alpha 0 over 2 plus summation m from 1 to infinity beta n cosine nx plus alpha n. So let me switch. So let me alpha n and then beta n sine nx be the Fourier series for f tilde, f prime, f tilde prime. Fourier series for large f tilde. Okay, this is now I have a function of t. Let's put this function of t instead of x. So I'm using here t and t. Okay. And they compute then alpha 0 equals 1 over pi integral minus pi to pi f tilde t dt. Okay. And then alpha n equals 1 over pi integral minus pi to pi f tilde t, and then cosine nt dt. And then beta n equals 1 over pi integral minus pi to pi f tilde t sine nt dt. And then also here, so what was the f tilde prime t? F tilde prime t was, here, this f tilde t, that would be ft minus a0 over t. So you can use this property to compute alpha 0, alpha n, beta n. Okay? So you can use integrals by part again. Okay? So by using integrals by part, okay, so what we can do is you consider this one, let's see small f small, this consider g prime, then f prime, oops, this one, let's see, I don't need to put this one again. So then let's call this g prime, then g t equals n 1 over n sine nt. Okay, so using integrals by part, so this alpha n becomes, so this is a derivative part that becomes this becomes 1 over, so you can just compute, so 1 over n pi integral minus pi to pi f tilde prime t sine nt. Okay, that's what you will get. Nt dt. So this is using integration by part. And then you put it in here. You put this guy over here, 1 over m pi integral minus pi to pi ft minus 1/2 a0 sine nt dt. So second integral becomes 0. First integral is just 1 over n minus 1 over n. This is bn. So this is what we have. Okay, so alpha n is just this one. And the beta n, you using integrals by part again. So what we have, this is 1 over m pi integral minus pi to pi f tilde prime. And then here you have cosine nt dt. That's what we have. And then again, you replace f tilde prime by ft minus a0 over 2, 1 over m pi integral minus pi to pi f of t minus a0 over 2 cosine nt dt. Again, second integral part becomes 0. So you can, and then first part, second part cosine integral of 0 because this is periodic function. And this one is just 1 over n, that is just alpha n. Okay, an. This is just an. So that's what we have. And then how about alpha 0? What was alpha 0? Alpha 0, let's see. And then we know that this guy converges. So by using Fourier theorem, that this guy converges to f pi, right? So here, so it's not easy to compute, 1 over pi integral minus pi to pi f tilde x dt, because f tilde given by this one, and so we don't know this one. So in order to compute alpha 0, so in order to get alpha 0, so we use Fourier theorem. So what we have here, what Fourier theorem is, alpha 0 over 2 plus n from 1 to infinity, alpha n cosine nt plus beta n sine nt. Okay, that is just large f tilde t. Okay, this is the Fourier theorem. This guy converges to f tilde, and this is integral minus pi to t fx dx minus a0 over 2t. Okay. So this is the Fourier theorem. Then in here we take t equals. Let's take t equals what? This is t equals minus pi. If you take minus pi, this term gone, right? You can also take t equals pi or minus pi. So I can take t equals pi minus pi. Let's go pi then. What happened? Then have alpha 0 over 2 plus summation n from 1 to infinity. So pi, then this one, you have alpha n cosine n pi. And the beta term is gone because sine n pi equals 0. Beta term becomes gone. So it goes, take a pi, then integral minus pi to pi fx dx a0 pi over 2. Okay, that's what we have. So then first part, this is the pi a0. This is a0 pi minus, so here minus 2, that would be a0 pi over 2. So that's what we have. So finally, so we have alpha 0 over 2 plus summation n from 1 to infinity. And then this guy is minus 1 to the n. So that would be alpha n minus 1 to the n. That becomes a0 pi over 2. Okay, so finally our alpha 0 over 2 becomes a0 pi over 2 minus summation n from 1 to infinity minus 1 to the n alpha n. So we have here. So then you can plug this one to here. Let's put over there. Then the Fourier series, then alpha 0. The final we are done. So alpha 0, let me use another color. So then alpha 0 over 2 summation n from 1 to infinity alpha n cosine nt plus beta n sine nt. And then you replace alpha 0 over 2 by this one. Then alpha 0 pi over 2 and summation. You have this part. That would be summation n from 1 to infinity. So alpha n part then would be alpha n part. So alpha n take outside, then cosine nt minus 1 to the n. Okay, and then plus beta n sine nt. So that's what we have. Okay, and then also so we know the alpha n. What was alpha n? So you replace alpha n by minus 1 over n. So alpha n was minus 1 over bn. Beta n equals 1 over n alpha an. So you just replace by that. Alpha 0 pi over 2 summation m from 1 to infinity. That would be alpha 1 over n bn, and then cosine nt minus 1 to the n. I got too many parentheses here. And the beta n 1 over n an sine nt. Okay, so this is what we have. Oh, so this I made mistake here. This is not alpha 0. This should be a0 pi. So this is also a0 pi. a0 pi divided by 2. So I just replaced alpha n and beta m. Okay, so that would be converged. This one is converged to integral minus pi to t f of x dx minus a0 over 2t. Okay, 2t. So this is by Fourier theorem. Then you can move this to the term left. Then a0 pi over 2 plus a0 over 2t plus integral n from 1 to infinity. And then I put over there, this one I put the same, and this one is converged to integral minus pi to t fx dx. Okay. Okay, so then this is the proof. This is the proof of our theorem. Okay. So this is you just rewrite that you will get this theorem. Okay, you will get this one from this. Okay, so a little bit longer proof this time, but it's not easy. No, it's not difficult. You can just apply Fourier theorem to prove this one. Okay, so let's stop now, and I will see you next time.